Here's another specific example of logistic growth. You might want to pause the video when you write this problem down in your notebook. The World Wildlife Fund has placed 1,000 rare pygmy elephants in a conservation area in Borneo. They believe 1,600 pygmy elephants can be supported in this environment. The number of elephants is given by 1,600 over 1 plus 0.6 e to the negative 0.14 t, and t is in years. How many years will it take the herd to reach 1,200? Well, here we have a logistic growth formula or function, and we know that the 1,600 is the carrying capacity because the WWF believes that 1,600 pygmy elephants can be supported in this environment. So that's where the 1,600 comes from, and these two constants are determined elsewhere. We don't have to worry about that. So in order to solve this, I'm sure you're aware, 1,200 is equal to 1,600 over 1 plus 0.6 e to the negative 0.14 t, and we're going to solve for t. So like we did before, when we cross multiply, we can just put 16 over 1,200. We're just going to exchange the two, the numerator and this denominator. So 1 plus 0.6 e to the negative 0.14 t is equal to 16 over 14 reduces down to 4/3. And so then we're going to just subtract 1 from each side. We're going to divide the whole thing by 0.6. We're going to take the natural log of each side. This is the ln of 1/3 divided by 0.6 to get rid of the e, and then we're going to divide the whole thing by negative 0.14 to solve for t. So we take our calculator and do the natural log of 4/3 minus 1 divided by 0.6, all divided by negative 0.14. So it's going to take about 4.198 years. And we can also do this graphically in our graphing calculator. If you want to grab your graphing calculator, you should have another logistic growth example in there, so you can just change up the numbers a little bit. So put the logistic growth formula into y1, changing the t and replacing the t with an x. And we're going to find out when the herd population reaches 1,200. So we put the left-hand side in y2 and the right-hand side in y1. We're going to have to change the window a little bit. Before we had, I think we had these for x min and max. But our y max will go up to 1,600. The horizontal asymptote is y equals 1,600, so I'm going to go up a little bit from that. I think I'll go up to 2,000. Anything above 1,600 would be fine. And when you graph that, I've already graphed it, so that's why mine comes up instantly. So there's the logistic graph, and there's the y equals 1,200. And in order to calculate the value of x, you're going to just second calc, option 5, intersect, enter, 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 and then you'll come up with the x value, 4.198. That's the same thing that we got when we did it algebraically. So here's the algebraic version, and this x value is what we just solved for, and they're identical. So I'm just showing you a logistic growth problem that you can either do algebraically using natural logs, or you can do it graphically by calculating the intersection of those two graphs. And that's it. See you tomorrow with a quiz.